All right, so I think we can get started. And since this webinar is being recorded, folks who are not able to join in today because of any previous commitments, they can always access the webinar online on our training sessions page. So with that, let's go ahead. All right, so hello and welcome to the webinar Building Performance Analysis and Optimization for Hospitals. I am Jayati, a building performance researcher at cove.tool with a background in both architecture as well as high performance buildings. So let's quickly get a look at what all we are going to cover today in this webinar. We are going to talk about how hospitals are different from other buildings and what are the key metrics to improve its performance. Further, we look into the workflow to optimize a healthcare project based on energy, carbon, cost, daylight, and we'll also discuss about an example. Finally, we will end the session with Q&A. So feel free to drop your questions in the chat so that we can take them up towards the end. All right, so with that, let's dive right into it. Climate action, I'm sure you have seen this slide before, but that's now it's all about that, fighting climate change. And buildings account for 40% of emissions causing climate change and 76% of electricity use in the United States. We are seeing new bills being passed in the Senate with funding, investment, and tax credits for energy efficiency and carbon reduction. So if you have not seen it, you must visit democrats.senate.gov to go through at least a summary of the energy security and climate change investments in the Inflation Reduction Act of 2022. What does this mean for us? This means we are going to see a drastic rise in an effort to make buildings high performance, which unfortunately should have been a practice all along. But specifically for hospitals, this can be a challenge, mainly because there are a lot of things to be considered in a hospital building, which makes it complicated. So here on the right-hand side, you can see a graph on energy codes, which show the energy reduction targets. And on the left are all the health and safety requirements for hospitals. So healthcare projects are unique because we are not just living and working there, we are trying to heal people there. And modern medical facilities depend on energy resources to treat patients, which means any reduction in building performance can compromise their health and safety. So it won't be as simple as just getting an efficient, mechanical system or switching off the lights. Now, another unique feature of healthcare projects is considering air pollution as a key aspect. Definitely when implementing strategies like natural ventilation, because creating a certain kind of atmosphere in hospitals is very critical, but also aligning with the main goal or objective of hospitals to do no harm. Thus, that's its main goals. Thus, for any healthcare project, we need to reduce the carbon impact. Now, these are just some statistics from 2021 to understand the scale of impact that we can see if we start improving the healthcare projects. Now, based on year 2021 numbers, there are more than 6,000 hospitals in US that you can also see in the diagram where they are densely located. Just under 1 million beds were staffed, which is huge. Admissions last year, which were due to COVID for sure, they were around 36 millions. And the total expense that includes all the cost is over $1 trillion. Now, another interesting fact is that between 2015 and 2021, that is in 6 years, 366 hospitals are being built very quickly to meet the needs of the patients. So now what's unique about hospitals when it comes to energy impact? It really comes down to how much energy they consume and how big they actually are. So hospitals account for only 1% of the built area, but contribute to 5% of the energy consumed from buildings. And this is a big difference between how much land they are occupying versus how much energy they are consuming. Another key aspect for hospital projects is that they take a long time to be constructed, anywhere between 5 to 10 years and sometimes even 20 years if it's very, very large. That means if we are designing for net zero by 2030, which is a goal a lot of firms have bought into, then the designs today, and in fact, some designs yesterday, should already be net zero. Now, what do we do in order to do that? So let's go through some key metrics you should consider when optimizing a hospital design, and also how you can leverage cove.tool in your workflow to reduce EUI, carbon, and cost for your healthcare projects. Now, these are the key metrics that you see on the screen that we are going to consider at early stage, which includes EUI, operational carbon, operating and capital cost, which means which means how much cost is required for operating the building and how much it will take to be built. Then the next is embodied carbon, then views, which means what can we see outside, how good are we making patients stay, and finally SD and ASC, which is the quality of daylighting you're getting in the spaces. So the image that you see, the colorful one, is from a BDP project. And a big focus in the conceptual or schematic stage was SDA ASC and views here to provide a good atmosphere for the patients to heal, even more important for hospitals than in other buildings. So the first metric that we are going to look at is EUI, energy use intensity. It is basically the energy use per area for the whole year. The units are kBTU or kilowatt hour per area per year. We usually get this through an energy model for existing buildings. You can also get it from the utility bills. So you can back calculate. And really, this is about comparing and benchmarking. So EUI allows you to compare buildings of different sizes to see how well you're doing and tracking towards net zero. So the goal is to bring energy to zero. We do not want buildings to use any energy, because then we won't have to pay for that energy. There are no carbon emissions from generating that energy, and that takes us to our future of zero carbon. So a bit about site and source, because this can be very important. So in this webinar, we are just going to look at the site energy because that's the more common one. And also cove.tool can provide you that information. So you must know what that means and how to use it. So if you ever see EUI mentioned and it's not specified as site or source, there's a very good chance it's site. Also, you do not have to know anything about your site or utilities to calculate it. So it's easier when you are just starting out in your conceptual stage or schematic stage. Now, there's an argument for using source that it's more complete and is location specific, which is true. And also it converts everything to primary energy only, which makes it more equitable to to compare. Now, a good argument for using site versus source is that zero site energy is equal to zero source energy. That means once you get to nothing for site, they will equal each other. So they work out in that way. Now, the next one we are going to look at is SDA. This is spatial daylight autonomy, or more specifically, it's a percentage of floor area that is receiving between 300 lux to 1000 lux of daylight, which is basically good daylight, for more than 50% of the occupied hours in a year. It basically means how daylit my building is, or how much time the occupants in the building will be able to see natural light in the building versus electrical lighting. You can do this analysis using computer simulation, which is a 3D analysis tab in the cove.tool platform, where you can see the the animation from. So here you can see all your context buildings are already generated, and then a daylight analysis is carried on. Now, why we want to do this? Now, there are a lot of studies out there that shows how daylight can increase productivity, enhance the mood, and improve the health of people. So specifically for hospitals, there are advantages around circadian rhythms, sleep patterns, alertness that are regulated by the daylight in a space. So there's a whole separate field with melanopic lux that you can look into if you're really interested to go deep into it. But maximizing the daylight into your building would be a great first step. Now, conversely, we have annual solar exposure, ASC, which is glare. Now, glare is when there is too much sun, too much brightness that hurts our eyes. So this analysis gives us the percentage of floor area receiving greater than 1000 lux for at least 250 hours per year. Our goal is to minimize the glare so that the occupants are comfortable, and also it contributes to reducing the cooling energy as well, because we will be avoiding any extra solar heat gains. Now, there are also other analysis types like radiation and sun hours that can also be used to, avoid any hotspots on the building envelope. The next one here is operating cost, for sure. Operating cost is dollars paid for energy use on site, or any other currency. You will again calculate this through a simulation or back calculate from your utility bills. Why it's important? Because there's a budget for each project. And when it specifically comes to hospitals, there is a huge spending associated with it. The image on the right is from Targeting 100, which I definitely recommend checking out. It's a good source. It shows that every dollar in profit equals to $20 of gross income. Conversely, any money saved on energy would be actually 20 times that. That means if you're saving energy money, it can go back into improving maybe patient care in hospitals, which is what matters the most. So the goal is to minimize the operating cost as much as possible, having savings. Now, another one is that is important for hospitals and is related to the quality of space is quality views. Now, these are based on lead view credit, which is a good way to quantify what these views are. Like, how can we even measure what a good view is? And this helps us look at our building to say if we have good views to the outdoors, to the sky, not obstructed by buildings, and it's properly defined in the LEED standard what is counted as a good view and how can it contribute towards people's wellness. So again, you can run this analysis in the 3D analysis page, and the goal should be to maximize the views. One caveat on this is it's very important to include internal partitions since they can block the views. So if you have a deep floor plan, it can be very impactful to look into it closely. A couple more here. Of course, dollars spent to construction and fit out building construction cost. How we can get it? Through cost estimators or contractors for sure. But you can use the optimization feature in cove.tool that you can see here. It is an automated way to get an early stage estimate and compare between different products and assemblies. So not every hospital is built by a private institution that is independently funded. They have, budgets and limitations on what they can spend, and they want to make sure every dollar is going towards helping patients. So again, the goal here is to minimize. The last two here are around carbon. So getting back to our emissions, operational carbon, it's our greenhouse gas emissions from the energy we consume on the site. It's going to be CO2e, which is CO2 equivalent. It's typically in metric tons or kilograms. You can calculate this using the baseline energy page in cove.tool. It's contributing to climate change, so we want to minimize and also that negative impact on the human health. So we want to avoid as much of this as possible to improve the health of the communities that the hospitals are located in. And now we have embodied carbon, which is definitely newer on the scene when it comes to a metric, but very much of an important one in the past 10 years for sure. And really, this comes down to as we emit fewer and fewer carbon emissions from operation of the building to the emissions that go into making the building now stand up for a lot more. So we want to minimize those as well. Minimizing the complete carbon life cycle of a building is what it aims at. So you can get this information from EPDs or from manufacturers. EC3 is a platform which is a great source for providing A1 to A3, that is cradle to gate embodied carbon information, which is also plugged in cove.tool's optimization feature again. And here the goal again is to minimize it as much as possible. So in a summary, we want to maximize our STA and views and literally minimize everything else. And that's going to get us the quality or high performing hospital that we want. So this is what we are going to see in our workflow using a case study as we go forward. Before we kind of get into the workflow, I wanted to provide some benchmarking information so that we can kind of see kind of where things are at. So this is just an example that one of my colleagues, mechanical engineers, gave me the 10 hospitals in Boston, ranging from 550 to 150. Now that's a huge range. Um, average EUI for hospitals around USA, the center one that you can see is around like 249. So we can say around 250. Now, where that energy is being used is a hot topic because this helps us target what we do need to change to reduce energy. So knowing the end use is very important here. So here in this pie chart is a breakdown for MGH Gray building in Boston. It's a very old building, but constantly renovated. So hard to say how old things are in it. So you can see equipment and lights is 21%, which is expected. And then reheat and heating is 26%. It's cold in Boston, so this is again expected. Some interesting ones are medical imaging here. We always think that medical imaging, because MRIs have a huge kilowatt demand, that is going to be a huge energy use. But comparing it to the entire overall energy use of a build of a hospital, it's actually quite small in this case. Very similarly, say the pumps are almost nothing, whereas fans added together, we get over 10%. So fan energy is very important to a hospital as well. For another look at that, this is a similar breakdown for a hospital on the West Coast in Washington. A newer hospital with lower EUI, but again, looking at the split of where the energy is being used, it's being used a lot in that reheat, like the reheat, and then a lot in our equipment and lighting together. So the equipment and lighting percentage combined is also almost exactly the same. So that's kind of flag up that we need to target this to reduce the energy for my building. But what's interesting about these two aspects is that they require coordination with the stakeholders of the hospital. So it's not that simple. Oh, I can buy a more efficient chiller or boiler and reduce these things. There needs to be coordination with the operations of the hospital to really make an impact on these kind of things. Similarly, we again see imaging as only 0.8%. So again, it's not really moving the needle in any way whatsoever. So now next, we are going to go through some early stage modeling. And this often looks messy. So this is just an illustration of how a workflow might look. So a lot of things we might want to do, like look at HVAC options with so many things to look at, envelope options, massing studies, operational, all these things. But they all are kind of a mess. We don't know which one to start with. Maybe we start with some envelope options, get some energy out, didn't do cost yet. And it's really moving us kind of disconnectedly away from holistic optimization. So there's no connection to how we are optimizing everything. So we are going to reorder this for this kind of example and start very methodically. So we start with just a few models for massing studies, and we look at site rotation. Then we move on to looking at several options for HVAC, envelope, and operation. And we are going to run it as bundles. So basically, you don't look at HVAC options alone, but HVAC, envelope, and operations together, get metrics out in energy, cost, daylight, all the things we were just talking about. And that's going to allow us to decide on an optimized design, very kind of holistic approach and very audit approach, which will help you know when you are doing a complex project like a hospital. So this is something that you can also change based on your workflows. And the case study that I'm going to show and the examples that I'm going to use will closely align with this workflow. So the example that we are going to use today for the workflow is a case study by EUA, which is an architectural and engineering firm, in collaboration with the RTM engineers. It was a typical medical clinic in Wisconsin, was used as the location. The baseline clinic was planned as 20,000 gross square feet located on a single floor. So it's not that big. This was in the concept design stage, and their main goal was to know and understand the impact of design decisions such as orientation, building form, etc. So in the conceptual design phase, so that they are able to like increase the space quality and buildings energy efficiency. So I'll try to take you through the entire workflow of optimizing a healthcare project using this case study as well as some other examples wherever necessary. So taking it from the beginning, once you log into cove.tool and start a new project, you're going to see this project information page where you have to enter some generic information. So there are 8 use types here, and hospital is one of those. Once it's selected, along with the energy code, the automated model inputs, all the model inputs will closely resemble the occupancy, equipment load, and ACH required for an outpatient hospital building. So this template is best used for non-24-hour healthcare facilities such as ambulatory care centers, but acute hospitals will need further inputs modified, which can be done using the custom templates in the platform. So in this case study, they did create a custom template for medical clinics. So parameters or inputs were established based on their older but recent EOA projects for multiple health systems in the Wisconsin market. But if you do not have any such reference, then using this hospital template would be the best option to go with. So the first step is to start with the massing. For this case study, a series of recent EUA clinic projects were studied and compared to create a baseline design. So the 4 plans that you can see here were the recent projects that were referenced, and they represent 4 system examples, like a traditional layout and then the double-sided exam rooms and so on. So what they did was they created a combination of these 4 layouts based on their experience to have their one baseline design. So they had a typical program that included like a primary care exam, rotating specialist exam, lab, imaging, rehabilitation, um, retail pharmacy, some meeting rooms and staff support spaces and offices. Also, they tried to be realistic with the glazing percentages for each elevation based on their previous, again, the previous EUA projects. So the following images show the 3D views and each elevation of the case study. So basically they went like for the south and west facade, they have continuous glazing with a window to wall ratio between 36 and 50%, while east and north elevations have punch windows with lower window to wall ratio ranging between 17 to 19%. Now, if you do not have any such previous references, and specifically in that particular location, because every location has a different climate and your design strategies would change, then an alternative and useful method would be to create different design or massing options and run analysis on each to compare and select the best out of those. So especially if you're going with a huge hospital building of around 400,000 square feet, um, that we created here as an example, you would have a much larger scope to experiment and have different massing options. To do that, you would run some baseline analysis like your EUI, your daylighting, cost, and carbon without changing any inputs or parameters. All the analysis for each model can be completed within 15 minutes on cove.tool, and you can also run these models in different tabs simultaneously. So here you can see I got the whole building site EUI for all 3 whole building percent SDA. Red sun just denotes that glare was over 10%. Just flags to mean that shading devices will be needed in future analysis. Then you can see the construction cost here is equipment costs only for envelope, main mechanical items, just for comparison's sake. The embodied carbon is again the primary envelope elements, again for consistent comparison. So now we have to keep in mind that at this stage, we are not trying to find the right answer for each. That cost is not going to be the exact cost that EUI is going to change, but we are trying to find a comparable answer here. Which option should I go for? Which option is the best one? And based on this initial analysis, now I can make a decision to pick one option that fits my project requirements and then go ahead and optimize it further. So how do we make a decision here when we have like a lot of data? So it's important to start prioritizing metrics. We saw several of them, but which one should you use here? So it's really about identifying the key stakeholders and getting their agreement and their buy-in on what's going to be required. So unlike an office building where there is an owner for the building or maybe the CEO, there's all these unique positions in the hospital and teams of people that need to have a say in how it's designed, how it's going to operate. So there's the nursing staff, the lab staff, radiology staff, surgeons, which have a lot of say in how things like operating rooms and stuff will function. The physicians, doctors themselves, it's important to think about the patients and what will they need, the operation and teams of the maintenance staff, and then of course the owners and the owner reps and what's important to them for operating the hospital. And then as far as regulations go, uh, most states will actually have an AHJ, which is the authority having jurisdiction, and they will have specific requirements for hospitals. Perhaps your particular states have requirements on energy savings in hospital, or have specific requirements about air changes in hospital that are slightly different than others. So those are very important to talk to and not what and know what they are. So if you can bring these stakeholders together and get them to assign priority to metrics, it can allow you to make various decisions. So in this EUA case study of a medical clinic, they didn't have so many stakeholders as I listed down, as you would have in a big hospital. And their focus was mainly on maximizing the daylight and minimizing the energy consumption for their building. They wanted to study the impact of different orientations on energy and daylight. And if not orientation, they wanted to understand what other factors would have a significant impact on the predicted energy use intensity. For some big hospitals, it can be carbon emissions, and for some, it can just be cost, because maybe they have a very small budget and they just need this hospital built to help undeserved communities. In which case, the final optimization would be different from what we are going to see here. For this case study, the focus metrics were daylight and energy, which meant they wanted to understand and maximize their SDA, which can be equated to patient well-being. And next, they wanted to minimize their energy consumption. So moving forward, the baseline clinic design was rotated to face the 4 cardinal direction and the midpoint between each cardinal direction here. So the smaller increments are not necessary, as cove.tool uses an average of each north, south, east, west orientation to calculate the variance from true north. And then a mirror image of the plan was also tested to understand the difference in the results. So it was found, and also as you can see in this diagram, which was created by that firm using the graphics from our platform, the baseline clinic was well lit along the perimeter here. Interior spaces consist of smaller exam rooms without access to daylight in the deep floor plan, which actually gave a result of a low daylight autonomy score, around 30% and below. So anything above 55% is considered good for any floor. Now, the design team located the office, waiting, and registration spaces in the areas that take the most advantage of the available daylight. On the contrary, large portions of the baseline clinic are shielded from glare due to small rooms and deep plans. So anything that you see in green is, not overlit. And perimeter areas with significant glazing that receive excessive glare when facing south and would require blinds for glare control. So the best ASC values are usually achieved with large glazing areas facing north, but it depends from location to location. So they compile everything in a summary, like in graphs. So from the summary of the results for all the orientations compiled in this graph, it was seen that the results for daylight autonomy, SDA, and glare showed a nearly parallel track for all orientations. The larger percentage of glazing to the south created the greatest glare from east to southwest. The least glare is achieved with the large glazing areas to the north, but this also results in the lowest daylight autonomy. So basically, the results indicated that building orientation has some impact on the predicted daylight autonomy and glare in a typical medical clinic, if not very significant. And it's important to keep in mind that this might not be the case for every project. So daylight autonomy varies by 3% from north to south in the baseline design. This relatively small variance across all building orientation indicated that the baseline design is reasonably daylit. It was not making a big impact. As expected, large glazing areas to the north provide the least unwanted glare and lower level of illuminance. Now, this could be offset with increased glazing or higher window to wall ratios to the south for more daylight while adding shading devices to reduce that glare. So it's a trade-off. Um, since the daylight autonomy is consistent across orientations, window placement should be driven more by the interior planning considerations for light and views. And where glare is an issue for a given space, blinds or even fixed shading devices can be provided. So the specific needs of healthcare planning often result in deep floor plans with little possibility of daylight. So you would see this in most of the projects that are hospitals or healthcare related. Maximizing daylight and views in non-clinical areas is always a valid strategy to improve the staff and patient experience. And so this study supports a strong daylight strategy, which could, drive the planning decisions. Now, moving forward to the energy consumption, they calculated EUI for different orientation as well by using the default inputs in the baseline page, and then compiled the results in graphs and table to study them. So this was the graph they created. The graph on the right is pretty constant, and also in the table on the left, you can see that delta for EUI is actually 0.39 when all the different orientations were compared. This implies that the results for predicted energy use intensity showed minimal variation across the different building orientations, finally, again, indicating that orientation has an insignificant impact on energy use for this building type with the current design. A design with significantly more glazing may show slightly greater variation by orientation. So where does this put us? How can we make decisions with this? Well, the important aspects of these models is that they offer comparisons, and that means they're not always conclusive. Um, this particular study showed that rotating a building did not have a big enough impact to make a decision, and that's okay. What I would advise is to always avoid the temptation to add decimal points. So if you look at the graph in the earlier slide, um, you will see I can definitely base my results on, the to base my design like base my results through the two decimal points, and I can say that this one is better and this one is not. But in reality, we have to remember how accurate these models are at this stage. So I see all of them are near 35 for each. From a comparison point of view, I'm pretty confident about the comparison, but anything more might just be noise. So filtering that noise is important for a good decision making. And so again, how would we make a design decision at this stage of the rotation of the building? It often comes back to those other design aspects. So in this case, the design team might have gone with their original orientation for the site that was based on the site features and context, and definitely taking into account the daylighting, which had some impact that we saw. And that's okay based on the results you get. So some helpful tips on doing these kind of early stage modeling is don't get sucked into the details. Reheat and dehumidification are the end users in a building, especially for hospitals, and they will have an impact on the total energy use. However, I will argue that the options we are looking at here with rotations, different massing on impacting those two end users directly. And so we know we need to study them later when we have the level of detail required. And by that, I mean, that's going to be like all the zones of the building and how the HVAC system is zoned and what's the source for humidification, all of that. And then we can study those things and minimize them But at an early stage, it's important not to get distracted by them and allow yourself to make decisions with the information you have. Again, getting into that buy-in on what the metrics are going to be to drive the decisions is important. If you have a project where you start out and you assume emissions is the most important, but you haven't got buy-in from the whole client team, that's the case, then your decisions can become null and void pretty quickly. So it can turn out that cost was the most important factor that needs to rule all decisions. Then it's important that modeling also meets the real world needs. And this kind of gets down to glazing. For EUA clinic, window to wall ratio studies can be beneficial to increase daylight and be responsive to the spaces created. But I wouldn't really run it for energy, because if I do that, by that principle, no windows is the most energy efficient for a building. For the EUA medical clinic, also energy was mainly driven by lighting and equipment loads that we will see in the later slides. Also to mention that embodied carbon and cost are other factors that they didn't take into account early on, but you can always take that if that's a priority for your project. So now we come to the energy and the breakdown. So the EUA design team understood the effect of orientation and massing on their daylighting and energy, which was their first goal. So that helped them decide on the orientation, which could not have been possible in the later stages of design. So now they collaborated with the RTM engineers to use cove.tool's energy modeling feature. It was used to find the more impactful factors on the whole building energy consumption. So first they saw the lighting load. They wanted to take advantage of all the daylight they were getting into the space. And the next logical step was to use occupancy and daylight sensors. However, given the cost of adding daylight sensors and overall energy savings, this strategy was less viable for low budget projects seeking the most impactful energy reduction. So finally, in addition to lighting power density, reducing the equipment, appliance use, and changing the temperature set points are other efficient ways to reduce the energy use intensity that they tried. Then moving to effective mechanical systems, because they had their engineers on board as well. A more efficient mechanical system to reduce energy use can actually lead to a higher construction cost. Heat recovery system was tested in this project and showed little energy savings. Orientation had more impact on EUI compared to adding that heat recovery system. So alternative heating systems like ground source heat pumps have minimal energy reduction, but they help with reducing the reliance on fossil fuels, especially when paired with solar on-site energy generation. So basically, we're just, looking at the options here and not making like a decision. Next, envelope usually has a great impact on healthcare projects. For this one, they increased the roof insulation value to R40, and that had a significant impact on the predicted EUI for the baseline project. It came down to 33.65. Increased wall insulation offers additional energy savings as well. But where possible, increasing the roof insulation has a priority over adding wall thickness for additional insulation. Then they also like increasing the glazing performance by going for triple glazing shows some additional energy savings here as well, but it also has a high first cost. So the team decided on a detailed study to determine if the added window performance would allow for a reduction in the heating load or removal of perimeter window radiation. So now, apart from manipulating single parameters, they also wanted to look at what would they need to go towards net zero. Here they were at 33.41 as compared to 19.03, which was the 2030 target. The 2030 target is usually 80% reduction from the baseline average. Now, to explore the net zero aspect, they started utilizing the optimization feature in cove.tool, looking at different options. Typically, the net zero goal cannot simply be met by increased insulation or simple changes like operational changes. Additional strategies are often needed to further reduce overall energy use. And by that, I mean renewables and so on. So here in this table, like there's a lot of information. You can see they explored options for different things, starting from cooling set point, heating set point, standard and adjusted. You can see their definitions in our help center as well. Then for the daylight sensors, they tried sensors, no sensors, and even partial sensors. Similarly for occupancy sensors. Lighting, they wanted to go with LED option and no LED options. Then solar panels, they had various options for that as well. And then the roof R value was different roof insulation and roof insulations were actually tried. Yeah. Then further skylight hue value. So again, they had some options to try with, and then the system type. Since their engineering team was on board, it was very useful for them to collaborate and know which options were feasible for the system types as well. And then the wall R value and glazing U value. So you can see these were the bundles that were created that were better behaving than the baseline. So you can see they could reach like lower EUIs, which were even in negative. And this highlighted one is the baseline one. So the cove.tool analysis actually showed them the best strategy for achieving significant savings is including on-site renewable energy as part of their design. The addition of 5,000 square feet of solar panels reduces the PEUI enough to meet the current 2030 challenge to achieve a predicted EUI below 19. It also showed them an option with 10,000 square feet of solar panels. And that showed them that it was possible to be energy neutral or even energy positive when combined with other insulation and operational upgrades. So you can also see the cost premium here. It's a bit blurred, but you can see that it's around 84,000. But you can also look at the payback. So at a very, first look, you might be, that's a lot of money added to the project. Maybe I do not want to go for it. But when you look at the payback period, it's actually not a bad option. And also while building orientation had minimal impact, as we saw on the energy use, it may have an impact on the effectiveness of rooftop solar. So thus, if they go for it, building orientation should be considered again, as it impacts the surface radiation intensity and renewable energy production for reducing overall energy use and reliance on fossil fuels. So to recap, EUA did a lot of work there where more than 2,000 models were run with all those combinations. So a traditional method might take us like 160 hours for the daylight, the glare, the facade, the HVAC, all of that. But in reality, all these studies using cove.tool can be done in essentially 8 hours and more or less based on your speed and kind of options you want to explore. So you can do this very, very quickly, and that's important to not only save your project's team money, save projects money themselves, but also to get answers into decision makers' hand when they ask the question. And that can go a long way to getting decisions made. If someone asked a question Monday, it takes you 160 working hours to answer that question. And that's, a couple of weeks away. They're going to forget that question, like what that question was. And suddenly they have different priorities, making that decision very, very hard. So if we can speed up that response time of answers to questions, we can really help not only the bottom line of projects, but also get those decisions made. So this was definitely a early stage. Now we must always, see what are the next steps that you can take. And that can be minimizing reheat, implementing heat recovery, reduce system loads. Um, Maybe not for the clinic, but definitely for huge hospitals. And good zoning of systems can actually have a greater impact on saving money and your energy for the building. So that's kind of all I had for today. Thank you everyone for listening in, and now we'll open it for any questions you all have.